Greetings, ladies and gentlemen. Welcome to the portal once again. Okay, so this is part 2 of lesson 7 of titrations. Okay, so this lesson focuses on the second part of the titration, which is the back titration, or what we can call the indirect titration. Okay, the indirect titration. So now, what is this titration? Remember, I've defined a direct titration in the previous video, which is part 1. Okay, so now this one, it is defined as follows. It is a method where concentration of the analyte is determined by reacting it with a known amount of excess reagent. The remaining excess reagent is now titrated with another second reagent of known concentration. Okay, so what happens here is that if we want to determine the concentration of the analyte, we can react it with a known volume of excess reagent. Okay, and then what is remaining of that excess reagent will now titrate it with what? With another solution with a known concentration. Okay, so there are different scenarios in this part of back titration. I will explain with an aid of diagram. Okay, so now when do we do a back titration? Okay, so we do a back titration if we have these scenarios. Okay, so now it is typically applied in acids and bases when the acid or base is insoluble salt. Okay, so for example, calcium carbonate, the base. So when the acid, or more commonly the base, is insoluble, okay, so mostly we can do a back titration. You will notice even when you will be doing questions that back titrations will include calcium carbonate and what, and acetic acid, or what we call ethanoic acid. Okay, so now again, when the direct titration endpoint is hard to detect. Okay, so for example, if we are titrating a weak acid in a weak base, or maybe we have added a weak base to a weak acid, you see, so it is going to be difficult for us to know the endpoint, because both of the weak acid and the weak base, they have a smaller amount of concentration in water. Okay, so the weak acid ionize incompletely, and the weak base also dissociate or ionize incompletely. Okay, so now another point is when the reaction occurs very slowly. Okay, so we can also do a back titration. So now this information, I got this information from a PhD research by Anne-Marie Helmenstein, yes, Anne-Marie Helmenstein. Okay, so you can go and search this document. I will link it in the description of the video. Okay, guys, so now what happens, for example, a back titration? Let's say I have a beaker containing 20 cubic centimeters of hydrochloric acid. Okay, so now I do not know the concentration of this hydrochloric acid. I only know the volume of this hydrochloric acid. Okay, so now I go on and take for example 1.2 gram of calcium carbonate, of pure calcium carbonate. Okay, so I take this 1.2 gram of pure calcium carbonate, I add it to the 20 cubic centimeter of hydrochloric acid. Okay, so now this calcium carbonate, it is completely used up by the hydrochloric acid, and then excess of the hydrochloric acid remains. Okay, so meaning now by the stoichiometric terms we say that the calcium carbonate it is the limiting reagent and the hydrochloric acid is in excess. Okay, so now this calcium carbonate will react with a smaller amount of hydrochloric acid, okay, and some excess amount will be left inside this beaker, some excess amount of hydrochloric acid. Okay, and then now let me use colors. Okay, so so this calcium carbonate, let me take this one. Okay, so this calcium carbonate, it will, let's say, consume about this much of the HCl. Okay, so let's say the HCl is white. Let's say the HCl is white. Okay, so now it will consume about this much, and then what will be left? What will be left is this. We'll be left with this much of HCl. Okay, of HCl. So now this much of HCl, the rest now, the rest what was there, it is now neutralized. Neutralized by what? It is neutralized by the calcium carbonate. Okay, let's say now this is neutral. So this smaller amount of calcium carbonate, when it was added to this 20 cubic centimeter of hydrochloric acid, reacted with smaller amount of this HCl, neutralizing it from being white to being blue. Okay, so now we are only left with the white, smaller than white acid. Okay, so we want to we are going to titrate the remaining white with what? With another solution. Okay, so going to do this now. So we are going to take this this solution with the remaining white HCl and put it below a what? A burette. Okay, holding a standard solution. Okay, remember what is a standard solution? A standard solution, it is a solution with known concentration. So now this standard solution, we know its concentration and we will know its volume. Okay, so in here we are going to add indicator so that we will see the end point of our titration. So now we are going to add the amount of this standard solution in here, and then until this reaches end point. Okay, so now what are we going to know from this? We are going to know that the amount of moles that were titrated by this thing. Okay, because we will relate with stoichiometry between the moles of the standard solution and the moles of the excess HCl. Okay, so we will determine that by neutralization by this formula. Okay, so this part will determine by this formula, and then we will know the exact concentration of this and be able to calculate the moles. Okay, so now what happens is this. If I can go back to this part, okay, what happens is inside this 20 cubic centimeter of hydrochloric acid, right, initially before I added calcium carbonate, I had, let me say, total moles of hydrochloric acid. Okay, let me write it a bit down. Okay, I had total moles of hydrochloric acid. Okay, so now inside the total mole of hydrochloric acid, what happened? Some of the moles of hydrochloric acid, they reacted with what? With calcium carbonate. Okay, so now I'm gonna say mole of hydrochloric acid reacted. Okay, reacted. So these moles of hydrochloric acid reacted, they have reacted with what? With calcium carbonate. Okay, and then after they were reacted with calcium carbonate, there was excess mole that was left. Okay, so now there's now mole of HCl in excess. Okay, so now we have an equation that give us the total mole of HCl initially that was in here. Okay, so now if I add what was remaining and what was used up by calcium carbonate, it will give me what was there initially. Okay, so now alternatively I can say this again. I can say that these ones, that the moles of HCl reacted with calcium carbonate, okay, plus the moles of HCl that were reacted with the second solution. Suppose this solution is sodium hydroxide, so I'm going to say moles reacted with what? With sodium hydroxide. Okay, so and then this amount of moles, this mole of HCl reacted with calcium carbonate, I'm going to have to use stoichiometry between calcium carbonate and HCl. Okay, and even this one I'm going to have to use stoichiometry between sodium hydroxide and HCl to get these moles. Okay, so in back titration we will mostly use this relationship. Okay, so total mole is equals to mole reacted plus mole in excess. This is what you are going to use, guys. Okay, so let's check an example. Okay, guys. Okay, so here's an example of a back titration question. Okay, so I could not find an easier one, because the textbook that I'm using does not have this kind of questions. Okay, guys. So now this one is from a previous question paper from 2020 November 2020 November, Department of Basic Education. Okay, now so let's check the question. It's saying that household vinegar contains 4.52% of ethanoic acid. Okay, so a 1.2 gram of impure calcium carbonate is added to 25 cubic centimeter of what? Of household vinegar. Okay, so notice this. Remember the pointers that I gave you. Now, which pointer is this? Is point number 2. When the direct titration endpoint is hard to detect, e.g., reaction of weak acid and weak base. Calcium carbonate, it is a weak base, and ethanoic acid, it is a weak acid. Also from point number 1, you can see that when the acid, or more commonly base, is an insoluble salt such as calcium carbonate, you see. So let's go back to the question. So now the 1.2 gram of impure calcium carbonate is added to 25 cubic centimeters of household vinegar. Alright, so now on completion of the reaction, the excess ethanoic acid is there. Is the excess ethanoic acid in the household vinegar is neutralized by 14.5 cubic centimeters of sodium hydroxide solution. You see, of concentration 1 mole per dm cubed. The equation of the reaction is that ethanoic acid and sodium hydroxide. Okay, so now I'm going to draw a scenario that what is going on. Okay, so now and then 7.2.1 they say calculate the number of moles of the unreacted ethanoic acid. Okay, before we can answer the questions, let's do this. So what happens is this: we have or let me choose a conical flask. Okay, so now in here we have 25 cubic centimeters of household vinegar. Okay, of vinegar. Okay, and then now in here they added 1.2 gram of impure calcium carbonate. Okay, notice this: you cannot calculate the number of moles of calcium carbonate from the mass directly because it is impure. Okay, so it has some impurities in it. Okay, so now, and notice that this is not 25 cubic centimeter of ethanoic acid, but it is 25 cubic centimeter of household vinegar. And in this household vinegar, there is what? There's 4.5, I think. Let me check. Let me verify. There's 4.52%. There's 4.52% of ethanoic acid. Okay, so now after adding this calcium carbonate has reacted with a bit of the ethanoic acid inside the vinegar. So it is reacted with a bit of the ethanoic acid, leaving some ethanoic acid in excess. Okay, so now this excess solution, it was now taken, and this excess solution, it was now taken and titrated with what? With sodium hydroxide. Okay, it was now titrated with sodium hydroxide. Okay, so and then this sodium hydroxide, we know its concentration. Its concentration is 1 mole per dm cubed. Okay, and we also know its volume. Okay, so now the concentration of this is 1 mole per decimeter cubed. Okay, they've also told us the volume. So what happens is this. Okay, what was in here, the total, what was in here, so we had total I'm gonna say total mole of what? Of ethanoic. Okay, total mole of ethanoic. Okay, so what happens to total mole of ethanoic? Some of the moles of ethanoic reacted with the calcium carbonate. Okay, so I'm gonna say mole of ethanoic reacted. Okay, and then after the moles of the ethanoic acid has reacted with calcium carbonate, so there was an excess amount of ethanoic acid. So I'm going to say the mole of ethanoic acid in excess. Okay, so this is our formula. You see, this is our equation. So we are going to work around this equation. Okay, so now the ones that are in excess, they are the ones that are being titrated by the standard solution. Okay, so we can also determine this excess moles by stoichiometry between the standard solution and the ethanoic acid. Okay guys, So back to the question. So we are given the equation of of ethanoic acid and sodium hydroxide. Okay. So now 7.2.1 they say calculate number of moles of the unreacted ethanoic acid. You see, number of moles of unreacted ethanoic acid. So which ones are the unreacted ethanoic acid? Remember, here I have the reacted and the excess. So the ones in excess, they are what? They are the unreacted moles. Okay, so it's a reacted and unreacted. So the ones that are in excess, they are unreacted. Okay, so now let me write it here. 7.2.1. Okay, so we are going to calculate excess moles. Okay, that's what they're looking for, excess moles of ethanoic. Okay, so now what do we know? We know that we are given the concentration of sodium hydroxide. Okay, so the concentration of sodium hydroxide is what? Is 1 mole per dm cube. Okay, and then what else are we given? We are given the volume of sodium hydroxide. Okay, so now the excess ethanoic acid in the household vinegar is neutralized by 14.5 cubic centimeter of sodium hydroxide. So we are given 14.5 cubic centimeters of sodium hydroxide. Okay, of sodium hydroxide. So now we are going to calculate the moles of sodium hydroxide and use stoichiometry to find the unreacted moles, or what the moles reacted with sodium hydroxide. So now N is equals to CV. Okay, so C is 1. Okay, multiplied by 14.50 divided by 1000. 14.5 divided by 1000. So you're getting 0.0145. Okay, so now the answer is the same thing, 0.0145 moles of what? Of sodium hydroxide. Okay, now but then again we are asked to calculate the moles of the ethanoic acid. We have calculated moles of sodium hydroxide. So how do we get moles of ethanoic acid? We use stoichiometric ratio because the equation is balanced. Stoichiometric ratio, so it is 1:1. Okay, so now I'm going to say it's 1 mole of ethanoic acid requires 1 mole of sodium hydroxide. You see, so it's 1:1. So now moles of ethanoic acid. Okay, so they are the what? They are the excess, which is the unreacted. They are the excess is equals to 1 multiplied by 0.0145. Okay, so why do I say 1? Because the stoichiometric ratio is 1:1. Okay, so still the same answer, 0.0145 moles of ethanoic acid. Okay, so now that was 7.2.1. What about 7.2.2? Now things are getting very serious now. So calcium carbonate reacts with ethanoic acid according to the following equation. So they've given us an equation there. Okay, so we can see that the stoichiometric ratio between the base and the acid is 1:2. Okay, and notice that here we have weak base and weak acid. You see, so now calculate the percentage calcium carbonate in the impure sample. If 1 cubic centimeter of household vinegar has a mass of 1 gram, okay, if 1 cubic centimeter of vinegar has a mass of 1 gram, okay, so now they are requiring us to calculate the pure mass of the calcium carbonate. How are we going to do that? Okay, so first of all, we need the moles of calcium carbonate in order for us to calculate the mass of calcium carbonate. Okay, so how are we going to get the moles? We have to know the moles of what? Of the ethanoic acid that has reacted with what? With the calcium carbonate. Okay, so in order for us to know the moles that were reacted with calcium carbonate, we have to know, so we know this one now, so we have to know the moles of ethanoic acid reacted. Okay, how are we going to know the moles of ethanoic acid reacted? We have to have total mole of ethanoic acid. So in order for us to calculate total mole of ethanoic acid, we have to calculate the number of moles of the total ethanoic acid. But how are we going to do that? We have to calculate the mass of ethanoic acid inside the household vinegar. Okay, so we have to do that. So because now we are given 25 cubic centimeters of household vinegar, we are going to calculate the 4.5% of that volume. After we get that volume, we know that okay, 1 cubic, for each and every 1 cubic centimeter there's 1 gram. So then we convert it to grams, and then from there we can calculate number of moles of the ethanoic acid. Okay, and then we will work out in that equation. Okay, so now okay, let me go back to the scenario. Okay, so now given that there's a 4.52, so mass, I'm going to calculate mass of ethanoic acid in household vinegar. Okay, so it's going to be 4.52 over 100. Okay, that's percent, multiplied by 25 cubic centimeters. Okay, and then now we know that 25 cubic centimeters, we are given a ratio that for every 1 cubic centimeter there's 1 gram. So multiply by 1 gram divided by 1 cubic centimeters. Okay, so now here we can see that cubic centimeter will cancel cubic centimeter, and then our units will be left with grams. Okay, so 4.52 divided by 100 multiplied by 25, so we are having 1.13 grams of what? Of ethanoic acid in household vinegar. Okay, so now with this, it means this is the total mass in this ethanoic acid before we added the calcium carbonate. So we can calculate total mole from that mass that we have just calculated. Okay, so now in order for us to calculate the moles, number of moles, we are going to need what? Molar mass. Okay, so number of moles is given mass over molar mass. Okay, so I have 1.13 gram divided by what is the molar mass of ethanoic acid. So I have 12 times 2 plus 2 times 16. Okay, plus 4. Okay, so I have 60. So I have 60 grams per mole. Okay, so now gram cancels gram. Okay, and then this per mole is going to go to the numerator to be mole. Okay, so now I have 1.13 divided by 60. Okay, so which is 0.0188 moles of what? Of ethanoic acid. Okay, so but what are these moles? These are the total mole of ethanoic acid. Okay, so total mole of ethanoic acid 0.0188. Okay, moles. You see, so now what do I have now in my little equation? I have the total moles. I have what? I have moles that are in excess. So I can say moles of ethanoic acid reacted is total mole minus mole in excess. You see, so now I'm going to do that. So mole of ethanoic acid, mole of ethanoic acid reacted, okay, is equals to total mole of ethanoic acid minus excess mole. Okay, mole of ethanoic acid in excess. Okay, so now the total mole, how much is total mole? 0.0188 minus mole of the excess mole. Okay, the excess mole we've calculated it here is 0.0145. 0.0145. Okay, so how much is the difference now? 0.0188 minus 0.0145. Okay, so now it's 4.3 times 10 to the power minus 3 moles. But moles of what? Moles of ethanoic acid. Okay, but remember, we are trying to calculate the the mass of calcium carbonate, and for that we need the moles of calcium carbonate. Okay, so now I'm going to use this equation. Okay, because now I have the moles of this, I need the moles of that. Okay, so what am I going to do now? Okay, so as you can see, I have 1:2. Okay, so now for 1 mole of calcium carbonate, 2 moles of ethanoic acid are required. Okay, so now you can see my stoichiometry is 1:2. Okay, so now which moles do I have? I have the moles of what? I have the moles of ethanoic acid, which is 4.3 times 10 to the power minus 3. Okay, then what do I have this side? This side I have x. You see, so now if I cross multiply, I'm going to have 1 multiplied by 4.3 times 10 exponent negative 3 is equals to x times 2, which is 2x. Okay, so now meaning x is what, 4.3 times 10 to the power minus 3 divided by 2. Okay, how much is that? It's 2.15 times 10 to the power negative 3. Yes, to the power negative 3 moles. Okay, so but they are the moles of what? Moles of calcium carbonate. So you can conclude it here and say mole of calcium carbonate is 2.15 times 10 to the power minus 3 moles. Okay, so now we are not yet at our final answer. Our final answer requires percentage purity. Okay, so meaning we need mass now. So now the mass of the calcium carbonate, how are you going to calculate the mass of calcium carbonate? So it's going to be number of moles multiplied by molar mass. Okay, so number of moles 2.15 times 10 to the power minus 3 moles. Okay, multiplied by the molar mass of calcium carbonate, which is 100. So 100 grams per mole. Okay, so you can see that mole will cancel per mole. We are left with grams. Okay, so we have 2.15 times 10 to the power minus 3 multiplied by 100. What do we have? We have 0.215 grams of calcium carbonate. Okay, so now remember they say calculate percentage calcium carbonate in impure sample. Okay, so we're going to calculate percentage carbonate in that impure sample. So now meaning we're going to say percentage of calcium carbonate in sample. Okay, in sample is equals to pure calcium carbonate divided by the sample. Okay, so multiplied by 100. Okay, multiplied by 100. So the pure calcium carbonate is 0.215 grams divided by 1.2 grams. 1.2 grams, because we are given 1.2 grams. Okay, we are given 1.2 grams. So now times 100. So how much is the percent? 0.215 divided by 1.2 multiplied by 100. Okay, how much are we getting? I have 17.9. 17.9 0.92%. 0.92%. Okay, so now this is the answer. Okay, this is how a question of a back titration could be asked. So I am sorry that I have chosen a difficult question because I could not get an easier one. Okay, so but then yeah, this is as difficult as it can get. It doesn't get any difficult than this. Okay, so yes, let's see if we can get another question, guys. Okay, okay, we got us another example that we can use. Okay, so this one is from a Free State 2016 trial exam. Okay, so it says calculate solution calcium carbonate solutions provide living organisms with the substance they need to grow their protective shells. and skeletons. For example, eggshells are composed of calcium carbonate, and Greathoff learners decide to calculate the percentage calcium carbonate in eggshells at STP. Okay, so they take 5 grams of crushed eggshells and rate it with excess hydrochloric acid according to the following equation. Okay, so the carbon dioxide gas produced is collected, found to be that. Okay, after all the calcium carbonate has reacted, calculate the percent calcium carbonate in the 5 grams of eggshells. Well, okay, this is not much of a back titration. It is more of a straightforward question. Okay, so we will do this one in the next video of answering questions. Okay guys, so let me add another one that I see that it's worthy for us to do as a back titration. Okay, so I found the question, guys. This is now the nicest question that we're going to do. Okay, so please be patient. Here we have a question. It's from the 2021 June exam, May-June exam. So as you can see, 7.3, it's worth a whopping 8 marks. Okay, so it is a good question, guys. So when I see this, I get excited. Okay guys, so now let's start from the heading. It says learners prepare a solution of known concentration by dissolving 2 grams of pure sodium hydroxide crystals now in water of 250 cubic centimeters volumetric flask. So if you can see the underlined word, a solution of known concentration, what is that solution? It is known as what? As the standard solution. Okay, is what we've been talking about. And then 7.2, calculate the concentration of the sodium hydroxide solution. Okay, so we are going to need the concentration of that sodium hydroxide solution, so we better calculate it very fast. Okay, so let's try to calculate. Okay, so now, okay, DBE 2021 May-June. Okay, sorry. Okay, so now we are given 2 grams and what the volume is, what it's 250 cubic centimeters. Okay, so the mass we are given 2 grams and then the volume 250 cubic centimeters. What about molar mass? Molar mass, we can calculate molar mass. It's molar mass of sodium hydroxide, it's 40 grams per mole. Okay, so now how am I going to calculate the concentration of sodium hydroxide? So I'm going to say concentration is equals to given mass divided by molar mass multiplied by volume. Okay, so given mass is what? Is 2 grams divided by molar mass 40 multiplied by 250 divided by 1000. This is 0.25. Okay guys, so now how much is my concentration? So my concentration is 0.2 mole per decimeter cube of what? Of sodium hydroxide. Okay, so I'm going to need that. Okay guys, so now the pH of the solution. So I'm not going to need the pH of the solution for now. There is a video of how to calculate pH. Go and check that video. of how to calculate pH. It's lesson number 4. Okay, so now learners, react 1.5 gram of pure calcium carbonate with 50 cubic centimeters of dilute hydrochloric acid of unknown concentration. Okay, so let me do this. Okay, so here's what they are doing. Okay, so they are taking here there's what there's dilute HCl solution, right? And then inside the dilute HCl solution they're adding calcium carbonate that is pure. Okay, so now they are adding 1.5 gram of pure calcium carbonate, and then the volume is 50 cubic centimeters. Okay, so the volume of HCl is 50 cubic centimeters, and this one is it's 1.5. Okay, it's 1.5 gram of calcium carbonate. Okay, so what's going to happen is inside this there's what moles of hydrochloric acid. So before they added calcium carbonate, what do we have? We have total mole of what? Of HCl. Okay, so now it's going to be mole of HCl reacted. Okay, reacted with what? With the calcium carbonate that is being added, and then after it is reacted there will be some moles of HCl that are in excess, that are left. So plus mole of HCl in excess. Okay, so this is our equation that we are going to use now. Okay, so notice that because this is a pure calcium carbonate, we can calculate its moles from this given mass. Okay, so now knowing the moles of calcium carbonate, we can calculate the moles of hydrochloric acid reacted using stoichiometry. Okay, and then this one, let's see what about this one. Okay, so now the excess HCl is neutralized with 25 cubic centimeters of sodium hydroxide that they prepared. Okay, so the balanced equations for the reactions are, okay, so here we have two hydrochloric acid and one calcium carbonate. Okay, and then we have the one of hydrochloric acid and sodium hydroxide. So when we have to determine the moles of the excess moles of hydrochloric acid, we are going to use this equation, and when we are going to calculate moles reacted with calcium carbonate, we are going to use this one. Okay, so now let's get on to it, guys. Okay, so let me write my data. So 25 cubic centimeter of sodium hydroxide. So the other information that I have volume of sodium hydroxide. They say it's 25 cubic centimeters, isn't it? Can verify. Okay, so now first things first, we have to calculate the moles of what? Of calcium carbonate. Okay, so we didn't even know here what the question is saying. Okay, calculate the initial concentration of the dilute hydrochloric acid. Okay, so in order for us to calculate the concentration of the dilute hydrochloric acid, now meaning that we have to calculate the total moles of hydrochloric acid in 50 cubic centimeters. Okay, and then after knowing these moles, divide those moles by this volume to get to the initial concentration. Okay, guys, so now when we know that total mole is given by mole reacted with calcium carbonate plus mole reacted with sodium hydroxide, they're the ones that are in excess. Okay, so now let me start. Mole of HCl reacted, okay, so it's going to be before I do that, let me calculate moles of calcium carbonate first. Okay, so mole of calcium carbonate, so I'm going to have mass, given mass over molar mass. Okay, so 1.5 gram divided by molar mass of calcium carbonate is 100. Okay, so 1.5 divided by 100, what do I have? 0,015. Okay, moles of calcium carbonate. All right, of calcium carbonate. Okay, so now that I know the moles of calcium carbonate and I know that stoichiometry between calcium carbonate and hydrochloric acid is this, so for every 1 mole of calcium carbonate there's 2 mole of HCl. Okay, so is 1 is to 2, you see. So now here I have moles of calcium carbonate, so I'm going to put 0,015. Okay, and then on HCl I'm going to put x. Okay, so now if I cross multiply, I have x times 1, which is x. I have 2 times 0,015. Okay, so what do I have now? I have 0,03. Okay, 0,03. Now what is this 0,03? 0,03, it is now the moles of HCl reacted. Okay, moles of HCl reacted, 0,03 moles of HCl. Okay, so now from this equation we can see that, oh, we have these moles. Now we are short of these ones. Okay, so now let's go calculate moles of sodium hydroxide. Okay, moles of sodium hydroxide. Now we know that we have concentration of sodium hydroxide in the volume of sodium hydroxide, isn't it? The concentration, it is the one that we've calculated here, is 0,2 mole per dm cubed, and then the volume of sodium hydroxide, it is the volume that neutralized the excess, so which is 25 cubic centimeters. So 25 divided by 1000 is what? Is 0,025. Okay, so now 0,2 multiplied by 0,025, the answer is 5 times 10 exponent negative 3. Okay, mole of sodium hydroxide. Okay, so now how am I going to get the moles reacted with sodium hydroxide, moles of hydrochloric acid? So now I'm going to say number of moles of in order for me to calculate number of moles of HCl in excess, I have to know stoichiometry between HCl and sodium hydroxide. Okay, so stoichiometry is 1 mole of HCl is to 1 mole of sodium hydroxide. Okay, so it is 1 is to 1. Okay, so now meaning that the number of moles of HCl in excess, okay, is equals to 1 multiplied by 5 times 10 to the power minus 3. Okay, so which is that? Minus 3 moles of HCl. So notice that we have moles of HCl here, and we also have moles of HCl here. Okay, so now total mole of if I calculate total mole of HCl is going to be that. It's going to be 5 times 10 to the power minus 3 plus 0, 0.03. Okay, so 0, 0.03 plus, okay, so what do I have? I have 0, 0.035 mole of HCl. So these are the total moles that were in this 50 cubic centimeter. Okay, so now I need to calculate the concentration. So now the concentration of HCl in 50 cubic centimeter is going to be number of moles, total mole, divided by the V. Okay, the V of 50 cubic centimeter. So now the total mole, as we have calculated, is 0, 0.035 divided by the volume is what? Is 50 cubic centimeters, and now 50 divided by 1000 is equals to 0, 0.05. Okay, so now what is the concentration? We're gonna say 0, 0.035 divided by 0, 0.05. Okay, we're going to get 0, 0.70 mole per decimeter cube of HCl that was in the diluted solution of hydrochloric acid. So now we have answered the question, guys, for 8 marks. Okay, thank you guys for tuning in, and sorry for the longest video. Okay, but this was very important. Okay guys, thank you. Don't forget to like, share and subscribe. Okay, ciao guys.